So I want to do the problem that you see bold-faced in red there, in which we are going to do a titration using HNO3, which is a strong acid, and this pyradine, which they give me the formula for, and they give me a Kb value for, so I know that that is my weak base. Now I could write that full formula out, but I could also just let my base be represented with a B, okay? Because a base is a proton acceptor, and if it's in there, I can easily show it accepting a proton from the acid. Now for the strong acid, I don't write the whole thing because most of it is a spectator ion. Anytime I work a problem with a strong acid, I let this be my strong acid. And down here, I'll tell you why. We know that when HNO3 goes into water, okay, it is a strong acid, so it will 100% donate its ion to the water and turn the water into this ion, okay? This is a spectator. It really doesn't involve itself in this reaction, but the HNO3 is supplying this part. So I just get myself in a habit whenever I've run across a strong acid to let this represent my strong acid. That way it's easier for me to show the proton swap that occurs. The acid-base, Bronsted-Lowry acid-base proton swap. So the base is a proton acceptor. When it accepts it, it's accepting an H+. So it becomes BH+. And what does the H3O+ become? Well, simply water. The strong acid drives it to completion, and I will do an ICF table representing it is going all the way to completion. Now, I'm ready to put some numbers in, and I keep in mind that this is a way of doing a limiting reactant problem, and I want to put moles into there. So let's get the moles of the base. The moles of the base, which is the pyridine. It would be the molarity of the base, which I see as 0.060, and I'll write it as moles per liter to remind me that I need the volume in liters. Well, this is an awfully big titration, okay? We got a big amount of base, 2.65 liters of it that we have got in this great big Erlenmeyer flask to do our titration with, and when we multiply those two numbers together, I have 159 is the moles of the base, and I can plug that in right here, 0.159. Now let's see what else they tell me. They tell me that I'm going to go to the equivalence point, and I want to know the pH at the equivalence point. They tell me what the molarity of HNO3 is, but they don't tell me the volume. That's okay at this point. I don't need to know the volume yet. By definition, being at the equivalence point means this number is exactly the same number as that number. So that is what I know. In the I-line, we have just put these in. They haven't had a chance to react yet in our calculation. We have none of this that's been formed yet, and we have water that we don't care about. In an ICF table, the reaction goes to completion until you use up the smaller quantity, which in this case are both the same. So we're going to use up that 0.159 and produce it on this side. Whenever you're at the equivalence point, these are always 0 because that's by definition what happens at the equivalence point, and you've converted all of your, in this case, base to its conjugate acid. All right? When you're at the equivalence point, you're going to have something here, okay? We look up here, and this something is a weak acid, all right? I'm going to put WA right next to it to remind myself that there is a weak acid that got formed, and that's all that's in there. And then I think to myself, well, how do you determine the pH of a weak acid? Well, what you do to determine the pH of a weak acid is you say that weak acid is sitting in water, and it is doing an equilibrium with water and generating for me something that I can use to get a pH. It's a proton swap, so the acid donates to the water. If the acid donates an H+ to the water, we're back to just having some B. So we've reformed some of this B that we had completely consumed earlier, and the H2O becomes H3O+. That's what acids do. And if they're weak, they do it with an equilibrium. If it's an equilibrium, then we do an ICE table, right? But what do we plug into an ICE table? We don't plug in moles, we plug in molarity because we have an equilibrium and our equilibrium constant expression uses that molarity. So as an equilibrium, I'll go ahead and write that the Ka is equal to the B concentration times the H3O plus concentration divided by the HA concentration. I will know that I'll need an HA, and I look at this problem and I see, well, they didn't give me an HA, Ka, they gave me a Kb. So I could get this guy by taking 1 times 10 to the minus 14 divided by the Kb. That's how I get a Ka. So I am going to, so 1.7 times 10 to the minus 9, okay? That's a pretty weak gas. I mean, that was a pretty weak base. So that's going to give me a Ka value equal to, let's see, what is it? I will tell you, 5.88 times 10 to the minus 6. Okay, all that because I wrote a weak acid equilibrium. I know this applies. I figure I need to know a Ka value, so I now have the Ka value for this. But now I'm ready to go back to my table. I said we need to put molarity into this table. What is this? That's moles. If I want to know the molarity of the BH plus, what do I need to know? I need the moles of BH plus, which I know, 0.159 moles, divided by the total volume, because I want to know the pH inside this flask, and it's got a total volume in there. Well, I know I have 2.65 liters of one of the things, all right, because I told you that I put 2.65 liters of this base in there, but I've got to put a volume of the acid. Well, it's not the same volume unless their molarities were the same. Are their molarities the same? Pyradine is 0.060, HNO3 is 0.447. Their molarities are not the same. So how am I going to get the volume of the acid so I know total volume? Well, this is a little subroutine I'm going to have to do, and I'll do that subroutine right over here. How about that? I know the moles of the acid. It was 0.159 moles. How did I know that? I knew it because it was at the equivalence point, and by definition these have to be the same. All right, that's the moles. What I want is volume. So I'm going to cancel the moles and go to volume. Moles per liter, flipped on its head. That's of the acid, so 0.447 moles are in a liter, and this will give me the liters of the acid that I put in there, the nitric acid that I put in there. The value for that number is 0.356. Not very much. Not near as much, is it, as the volume of this guy, because concentration was so much higher. But I'm going to put that here, 0.356. And now I can have the molarity of this BH. It gives me 0.0529. That's the molarity of the BH plus solution. Now, at any point you get lost, you got the benefit of stopping, rewinding, and go through that again. But what are we going to do with this number? This is the initial concentration of this weak acid, 0.05299. Don't care about this. This is 0. This is 0 before it has a chance to happen. Some of this gets consumed because it's an equilibrium, not all of it, and I end up with 0.05299 minus x. My pen's starting to get funky on me. See if I can get it to write a little bit better. Minus x, this is going to be x, and this is going to be x. So now I've got an expression. I've got numbers to fill into that expression. So I'm going to take what I see here and plug all the numbers in. Ka was 5.88 times 10 to the minus 6. That's Ka. B's concentration is x. H3O plus's concentration is x. And HA's concentration is 0.0529 0.05299 minus x. Okay, we look at our k. It's a small k. Let's make an assumption. Let's assume that x is much, much smaller than the initial concentration of that acid. May or may not be true, but we'll assume it so that we can ignore that x. We're going to get rid of it there with a little delete mark. Now, what we have, solving for x, it would be 5.88 times 10 to the minus 6 times 0.05299. That would equal x squared. And if we took the square root of it all, okay, that would give me a value for x. So in this case, the x value is equal to 5.58 times 10 to the minus 4. So we check our assumption. Is that much, much smaller than that? Well, to this many decimal places, it might make a difference, but that is very small compared to 0.05. 0.0005 is much smaller. So now that's x. We go back to the problem. It says to find the pH. What is x? Well, it's not the pH. X is the H3O plus concentration. So how do I take the H3O plus concentration and get the pH? Well, we take the negative log of that number. So the negative log of 5.5 times 10 to the minus 4 is equal to the pH, which is 3.25. Now before we leave the problem, and we have that 3.25. Before we leave the problem, we ask ourselves, does that make sense? When you do a titration where the base is weak and the acid is strong, you expect the pH to be less than 7. Okay? Why? Because at the equivalence point, all you have left is an acid. And so it should have a pH less than 7.